All right, so Chapter 10, alcohols, ethers, and other similar oh, I see. Yeah, it's never too early for the organic chemistry of alcohols. Yeah, it's 5 o'clock someplace, and they're probably doing organic chemistry too. So I know.
I think that's Paris. Is that 10 hours? No, that'd be 6. So then whatever's Norway.
We need 9
Norway.
hours.
So
there we go.
London? No, London's in that same time zone.
So
Is that mostly ocean? It's mostly ocean then. Dude, you missed the line.
that's what we're doing. We're doing alcohols at 8:35 in the morning. That's what we're doing. So this is going to be a little bit different, but there's going to be a lot than the mechanisms we've been doing. But there's a lot of similarity too in terms of principles. So what we've already kind of talked about is leaving groups as a concept, and alcohols in particular are poor leaving groups. So if you have an alcohol and you have this hydroxide functionality, for this to leave requires forming a hydroxide, which is basic, and highly basic things are typically poor leaving groups. So this is an example of a poor leaving group. Another poor leaving group would be, say, an ether, where to leave we'd be forming an alkoxide. So this is another great base, great nucleophile, poor leaving group. And because of this, it's very hard to do nucleophilic attacks. Because for nucleophilic attack to be successful, you have to have great nucleophile and a great electrophile, but there has to be the ability to break this bond so that we don't exceed our octet. And if you have something that's a poor leaving group, you have to do something with it first before you can undergo a nucleophilic attack. So let's see. So if we've got methanol and in the presence of hydrobromic acid, what happens? Let's see, how much detail do we want to do? It's 2 steps. We have a reversible process where the hydroxyl group reacts with the hydrobromic acid. And that puts an extra proton and positive charge on the hydroxyl group. This is a pretty darn good leaving group, because if you take these electrons and you push them over to the OH2+, by breaking this bond and putting those extra electrons satisfying the positive charge, what you're getting is water as a product. So this is a poor leaving group. This is a great leaving group. So just by the addition of the acid, we're able to convert a portion of the hydroxyls into good leaving groups. And then, in the presence of heat, we can get a nucleophilic attack with bromine and convert the alcohol into the alkyl halide, plus water. So we're going to go through the mechanism here, but in terms of rationale, why would we be interested in taking an alcohol to an alkyl halide? Some of it is just a function of convenience, really. So alcohols as a reagent are abundant and relatively inexpensive. So if you want to make an alkyl halide, we have a couple tools that we can do that. So we've got a bunch of reactions, substitutions, SN1s and SN2s with alkyl halides also. So if you're starting with an alcohol, you can go to an alkyl halide. From the alkyl halide, you can easily go to tons of other substitution elimination products. So let's look at the mechanism here and just a touch more depth. So we've got our methanol, and we've got hydrobromic acid, and this could be any alkyl halide other than hydrofluoric acid. Hydrofluoric acid's not great because this has to be leaving group 2. We already know fluorine's not a fantastic leaving group. So what can happen here, this lone pair from this hydroxyl can do a nucleophilic attack on this hydrogen, exceeds the duet, pushes the extra electrons to the bromine because it's a good terminal leaving group. And this is reversible because we can also go back doing this opposite reaction. Going to get rid of the plus because plus is next to a minus, makes it a little harder to see what's going on. So notice we're neutral here, but what we've done, we push these electrons onto the bromine, now we have a negative charge. So because we have a net neutral system here, we still have to be net neutral on the other side of the reaction. So we have a negative charge here, and because this gave up its electron to grab that proton, or sole ownership of it, we get a positive charge on that oxygen. And if you guys are kind of remembering the shortcuts for formal charges, oxygens are always 0 formal charge. If they have 2 bonds, 2 lone pairs. If you have 3 bonds, 1 lone pair, it's always going to have a +1 formal charge on it. So once we've got this, we have a good leaving group, and with the presence of a little bit of heat, we can get a nucleophilic attack where this bromine attacks back of the methyl group, pushing off the electrons to satisfy that positive charge, making water as a product, and that's how we get our alkyl bromide and water as a product. A couple notes about this. All 3 categories of alcohols, primary, secondary, tertiary, undergo these nucleophilic substitution reactions. If the alkyl halide that's attacking is coming in the form of hydroiodic acid, hydrobromic acid, or hydrochloric acid. So you can use hydroiodic, hydrobromic, hydrochloric for this, but can't use hydrofluoric. Just not good enough at accepting electrons on this side of it to really kick off the reaction. Since this is reversible, that really matters a lot. And the same rationale that we talked about here, poor leaving group with a hydroxyl. Once we protonate it though, now leaving group is water, fantastic leaving group. And that really drives the reaction. Let's see. Other details associated with. Any questions? Yes.
What do you need the heat for? It's like the reaction go fast enough to be significant?
Yeah. The heat's also going to favor the formation of this on the other side, because this is all happening simultaneously. So the extra heat's also going to help drive the formation of the cation, because a little extra energy is going to help overcome that barrier. So it'll shift equilibrium in this direction a little bit too.
Does that mean you should have the heat in both steps?
Hmm?
Does that mean you should have the heat?
Well, heat's the reagent that makes that take place. But yeah, it's this is all one step. So you have methanol, you add hydrobromic acid, you reflux under heat, you get how it comes. So if you were to describe this as one step, it would be some alcohol in the presence of hydrobromic acid with heat. And the reactant's the solvent too, in this case. So you can describe it in one step. Because it's like one pot, not multi-step. Other question? Okay. So let's see here. Notice we said nucleophilic substitution. Would this be SN1 or SN2? This is SN2, right? So this mechanism is SN2. I just said that we could have nucleophilic substitutions with primary, secondary, or tertiary. So would this mechanism apply to all three of those? One of these, two of these?
It applies to all.
I think it applies to primary.
Oh,
Most vigorous with primary, also works with secondary. Primary can go without heat because it's such favorable reaction for primary. For secondary, you need the extra heat to get it to go. Significant, like with any reasonable rate of reaction. Now, tertiary, we're going to be looking at an SN1. So let's look at the SN1.
So tertiary doesn't undergo SN2 usually?
No, because of steric interaction, steric issues with accessing via nucleophilic attack. And this is very similar to what you would see for your classic SN1, except the modification is what's the criteria that you need for an SN1 reaction, typically. You need a great leaving group, exactly. And you need to have a stable carbocation. So, if you have
So the water that forms is going to spontaneously leave.
good guess. Yeah, because this isn't going to work. Because even though it's tertiary and can support a carbocation, this will not spontaneously leave because hydroxyl is a terrible leaving group. However, if you put it in the presence of hydrobromic acid, this can do a nucleophilic attack first, grab this hydrogen, kick off bromine as a leaving group. And now we've got an equilibrium with a product which has an excellent leaving group. This can spontaneously leave because it really wants those electrons because the product is nice and stable. And then we've still got the bromide hanging out, which can do our next attack and get us our product. Let me redraw this over here, make a little bit of room. Now, the thing is you can also undergo an elimination reaction here. However, because we have a substituted alkene, well, yeah, you're going to get the same product exactly. So basically we have two different routes to the same product with the same reaction mixture. This does bring up a really important point though. Carbocations are can undergo both our substitution and elimination reactions, and carbocations are subject to, let's just call them shifts, whether that's a hydride shift or a methyl shift. So if you were doing this type of reaction and you had the ability to rearrange to get a more stabilized carbocation, that would take place. It's just like all of our carbocation-based mechanisms. So there's some problems with this particular approach. So, question, why don't we see elimination in the SN1 as a competing mechanism?
Wait. To the SN1? Did we see that?
Oh, sorry, the SN2.
Thank you.
SN2.
Because-
SN2. This is the SN1. Yeah.
Carbocation is not stable enough.
There isn't a carbocation.
Yeah, there's no. Because it's on the S.
It's not stable enough.
But, yeah.
But we have a mechanism of elimination that doesn't involve carbocation. For an elimination to take place, it has to act as a good base, right? And in this particular case, our solvents are going to be polar protic. And because we have polar protic character, we're not going to have phenomenal activities of bases. So the bases won't be able to function as strong bases. So in that mechanism, we're not going to have an elimination as a competing mechanism. Oh.
In the step where the OH2 is dissociating, is that going to be a slow step? Because you have it drawn as
Preferring the middle. Yeah.
drawn as like even, like between steps 2 and 3, when you have the formation of the carbocation.
Here?
Yeah.
This is reversible.
It's reversible, but is it slow like in like without in non-alcohol?
Yeah, because if this was in the absence of this, this is where you would normally start this mechanism, and that's your slow reversible step, which is rate determining, which is why it's SN1.
Yeah.
So that's your slow step.
Even in there, so it's just double check.
Yeah, so this is a slow step. And that's going to be your fast step with your subsequent attack. Do that. Let's see here. One other clarification. If we're looking at the SN2 on a primary, if you're doing this reaction, this works just fine if X is iodine, or excuse me, hydriodic or hydrobromic acid. It's okay for hydrochloric. Hydrochloric's a little slow. You can speed it up by using zinc chloride as a catalyst. So if you throw some zinc chloride in there, it'll get it up to snuff. The thing is that even though these are really simple reactions, as the compounds get more complex, just adding strong acid to the mix is often problematic. You very commonly, when you start putting strong acids into reaction mixtures, have unintended or undesirable consequences associated with that. So right here we have a single functional group that we can focus on, but in reality, adding strong acids often causes rearrangements. The strong acid will start pulling protons that you didn't want to pull off of a compound, and you can get all kinds of byproducts associated with that, or sometimes those byproducts are actually become the preferred reaction. So it's between that and the fact that you can get carbocation rearrangement if you have a tertiary setup, there's better ways to accomplish the halogenation of an alcohol. So the two that the book talks about, well, three, but two are practically identical. Let's see. Other ways is, let's see here. I just jumped the gun. Nope, didn't do it. Okay. So the first way are to use phosphorus trihalides. So this would be PBr3 or PCl3. Yeah, or PCl3. And either of these will put a bromine or chlorine substituting for a hydroxyl group. The other one is thionyl chloride treated with SOCl2. And SOCl2 is a really good way to put a chlorine in also as an alkyl group in substitution for a hydroxyl group. So let's look at these two reactions. I'm just going to talk about this one as a single reaction because the mechanism is identical. But of course, if you want to substitute bromine, you need to use PBr3. If you want to substitute chlorine, it's PCl3. Okay, so phosphorus is light in electrons here, and because of that, it can act as an excellent electrophile. We have a pretty decent pair of electrons here that can act as a moderate nucleophile, and we have phenomenal leaving groups in our bromines. So we have all the needed components to do a nucleophilic attack first with a hydroxyl group hitting phosphorus, kicking off a bromine, and what this does is it's analogous.
Is that just making it a better leaving group than water alone?
Exactly. Well,
Or
yes, it's it's a great leaving group, and we can get away from our need for a strong acid. So what happens here is this is in 2 steps, or not 2 steps, but let's say we want to do this reaction, we would draw it up as our ethanol, and we would use our phosphorus tribromide in pyridine as our solvent. And pyridine is a conjugated 6-membered ring with a nitrogen in it, which is super nasty to work with. It's one of the, when I worked in an environmental lab for a while, I had to do this particular reaction with highly acidified pyridine. And even though it took place in the fume hood, I had to wear a mask in addition to working in the fume hood. So I had to shave, which was awesome. And they preferred that guys do the reaction because pyridine's been demonstrated to bioaccumulate in women's reproductive organs specifically.
that's supposed to be CH3, CH2 behind your head.
CH3, CH2. That is a CH3. Not supposed to be. It is. Yeah, exactly.
It was never a CH2.
That's right. I'm glad that we're seeing eye to eye on this. So we've got our pyridine, and pyridine is a pretty darn good base, so it can swoop in, grab this proton, break this bond, pushing those electrons up to satisfy the positive charge, and the pyridine will be kind of consumed and acidified as part of this reaction. That's okay because it's a solvent and there's a lot of it, so it will not be limiting. And then from here, you can come in with the bromine. And any guesses? Nucleophilic attack where?
On the back of the
Backside attack. I like it. Come back over here. And if it was chiral, it would invert the chiral center. This example is achiral, so it doesn't matter. So this mechanism is the same whether it's PBr3 or PCl3. And the crux of this is we get to do the same type of thing where we enhance the quality of the leaving group so that we can do nucleophilic attack without having to use high heat or really strong acidic conditions.
So does this only happen with primary alcohols, or can it also happen with secondary?
Primary and secondary. Yeah. Primary and secondary because the tertiary still struggle with the nucleophilic attack on the backside. So thionyl chloride also takes place in pyridine. We had a guest lecturer at one point who was teaching this section out of a different book, and he was really aggravated because he came in with his stock lecture notes, and it was an on-the-ball group, and that particular book didn't teach the use of thionyl chloride for reacting secondary alcohols, even though it's fantastic and commonly used. Every book just, there's lots of reactions, and the books just choose a subset of reactions. They don't necessarily get all of them because there's way too many reactions to just include in every 300 level textbook. So, but he was really aggravated because he started talking about thionyl chloride in his lecture, and the students were like, what? It's like, oh, thionyl chloride. He hadn't looked at the book to see what the students were exposed to before doing lecture, so he looked a little silly. But then he talked about thionyl chloride anyway, and students like, oh. And then students were like, Dr. McGill, are we allowed to use thionyl chloride in our synthetic schemes? I'm like, yeah, as long as it's right, you're allowed to use thionyl chloride. So thionyl chloride, just use methanol. Let's see, SOCl2, yeah. Okay, so we got our thionyl chloride, which is SOCl2, and we're going to be doing that reaction in pyridine. So these are particularly great, both of these for secondary, because even though you can get the reaction to go for primary, if you don't have any acid-sensitive secondary groups that you need to worry about, you're definitely going to have improved yields and specificity by using these techniques, especially for secondary. So let's see here. The book shows this happening.
You said the book says, are you bothered by that?
I think there's a competing mechanism there, but we haven't talked about ketones, so this is reasonable approximation of the mechanism. The idea being, when we come in here, do this attack, we have an octet. This is starting to exceed the octet. So the question, if we were getting picky, is it easier for this sigma bond to break and send the electrons over to the chlorine? I guess there's probably multiple competing mechanisms. This could be direct, or we could push these pi electrons up to this oxygen, and then they could come back down and push. either way, we're getting a nucleophilic attack on a sulfur, and we're kicking off a chloride. So in the end, the result's the same. So it's just unusual to see anything do a nucleophilic attack on something doubly bound to an oxygen and not see the electrons get pushed to the oxygen. Which next semester you guys will be doing a lot of. It'll become like you'll see why it's a little odd not to see it now. So let's see, what do we get here? We get this reversible process. It starts a little bit far over. Let's see how this. So now you can see we have this charged system, just like last time, and just like last time, we're going to have a solvent, pyridine, swoop in, pull that proton off, push those electrons to the oxygen to satisfy the positive charge, and now we have a non-charged, high-quality leaving group. And now we can come in with our chloride and do backside attack, kick off our leaving group, and get our ethyl chloride as our product here. Oh, plus SO2 plus. We have extra Cl. Okay. So sulfur dioxide has a leaving group. Oh, I misdrew this. Excuse me. So this decomposes to sulfur dioxide and chloride. And just like H2O is a fantastic leaving group that's nice and stable, sulfur dioxide is a fantastic leaving group and stable. And additionally to that, is sulfur dioxide under normal conditions, solid, liquid, or gas? Gas, right? Smells of, right? Sulfur dioxide is gas. So in the reaction, if you have some reaction taking place, and you produce gas in the reaction, the gas leaves the system. That's removing the product via Le Chatelier's principle, which drives the reaction aggressively towards products, which is one of the reasons this is such a fantastic way to put a chlorine on a secondary alcohol. Yeah, right? So yeah, so unlike water, great leaving group stays in solution. So, particularly good for secondary alcohols because they're difficult to react, or more difficult than primaries. So there's examples on a primary, but we could have done it on secondary just as easily. I'm going to skip the sulfonate esters for now and probably come back and do them because sulfonate esters like tosylates are super useful for intentionally adding a semi-stable leaving group and what they're going to be used for. And I don't want to introduce them right now, but along these lines where you modify the hydroxyl group to make it an excellent leaving group. And then you can use any number of nucleophiles at your discretion to do a nucleophilic attack and kick it off. So it's a really important reaction because it's important for a lot of syntheses, but it's rarely the final product in a scheme. So we're going to push it back to next week. Any questions so far? Everyone's like, oh, this is exactly what we've been doing with like an itty-bitty twist. And if that's what you're thinking, hopefully you're thinking that not, ah! If you're screaming inside, you don't have to admit it right now. You're all faking it really well if you are. If you're like, yeah, this is pretty much exactly like what we've been doing, that means we're making excellent headway because you're starting to see the overlap in the rationale. And despite it seeming super complicated at first, I guess OChem is not as complicated as it initially appears. Until it doesn't work. And then it's super complicated.
So with that one, it's okay to draw one part of the mechanism the
Mhm.
same way, even though oxygen usually what you were saying. It's fine to draw it that way. You were saying that the electrons will push the oxygen. That's like another way. to
Oh,
draw
just
it.
draw. Yeah, you can just draw it with the. I said there's probably a couple different competing ways you could rationalize kicking the chlorine off. So just showing that the electrons are coming into the sulfur and kicking off the chlorine. Since the chlorine in the end is acting as the leaving group, that's fine. Yeah, you can do it just like the book did. Okay, so we just did substitutions of alcohols. Any guesses as to what comes next? Yeah, elimination of alcohols, right? So, you guys are like have the like flow of this figured out. Oh, segue. Who here put their name on a petition and sent it to the dean of CAS? Because it kind of worked. Yeah.
You said kind of. What's the stipulation?
So apparently it landed on somebody's desk, like the dean, on Friday morning. Finally made it, and then I started getting emails from the dean and the seniors and associate dean. They're like, hey, can we make this happen? Like, you seriously? Like,
We've been asking for how long?
well, not only that, but like with what, right? Because we need people. That's why I requested people. And I'm like, well, can we get an adjunct? And right. So and shuffle the schedule.
Maybe I can teach the 105 and 6.
You still need to have doctorate. I mean, you can get by with a master's in experience, but we also, it was like this piece of the puzzle. So I ended up talking with, because we had a couple ways we might be able to make it work without having to change class times. And without going into all the details, Dr. Acharya decided to just volunteer to do an overload to offer Biochem 1 next semester. So, it's not on the books yet, but it looks like we're going to offer Biochem 1.
Good job, guys.
Yes.
Good job.
Yep. So, it's going to be...
Whoever accidentally made it, like, land on that guy's desk.
So,
It's not an accident.
it wasn't an accident. In fact, it landed on a bunch of dean's desks before it got to his desk, because it'd take it to the dean's office, assuming everyone would know that would mean the dean of CAS. However, I forget that we have lots of deans, like there's the dean of students and there's the dean of College of Health, and they both ambushed the dean of CAS at the Council of Deans meeting, and he's like, what? Because he hadn't heard yet.
The lines of classes here? Wait, what?
Yeah, so expect that to show up
Interesting.
on the schedule. I don't know when it will be. It will be sometime that works in Dr. Acharya's schedule, that has her not running across campus necessarily. So, but that is a thing. So since we had 28 signatures was the count, hopefully we actually get some people in the class.
Well, we've all like planned our schedules and registered.
I know. But if you have to have it, it sounds like it's going to be available. Also, don't be the cry wolf person who's like, I have to have it, and then like 5 people sign up, because then it won't get offered. Yeah, exactly. But that's all I know about it so far, because I haven't had time to identify a time that works in Dr. Acharya's schedule and that hopefully doesn't interfere with too many other upper division classes. but there will inherently at this stage be some type of conflict somewhere with something.
Then, like, is there like a way that we should, like, do we have to like go to our schedule and registration thing and just like keep looking at it until it finally
I'll try to give everybody a heads up, but it won't fill up.
Well,
So there's no chance of it filling up.
yeah, but still, like, I don't want it to be like low registration because we just didn't.
No, you'll it should be up. Actually, it takes, depending on things we have no control over, it usually only takes from time of approval 2 to 3 working days for things to get added. Usually.
So should we still be looking at registration then to do that, or?
Yeah, you'll do it through registration.
Got it. Okay.
Was this the
Is
like?
it also on the docket for the summer too?
It will be on the docket for summertime. So, but that's not posted yet. So that's going to be offered through the College of Health, and I'm going to be teaching that one.
Oh,
Unless College of Health reneges, but I don't think they will. They've been pretty supportive of it. So.
Yeah, they have a lot of people that now have to take it as part of their degree.
I said, well, they wanted to get the Idaho State pharmacy students.
Yeah, and that's why they're supporting it. Okay, so that was the news I was originally going to start lecture with.
Well, thank you.
So, looks like advocacy works.
Is the same one like just scrolled on like a piece of notebook paper?
Huh?
Is it a petition that was just scrolled on a piece of notebook
No, that had 20 people or so from this class, but another petition with a whole bunch of other names.
Oh.
Yeah. No, that one's still in my office.
Why you didn't?
I
didn't even matter.
No, I took it to a meeting to show people that there is a list of names of people who wanted a class, and pretty much everyone collectively
Was it in an envelope?
was in. No, it was in. It was like wait yeah.
Envelope. I had
Like,
this envelope.
look, we have rabble rousers who are rousing with rabble and being generally cantankerous, wanting these classes for some reason.
like a graduation.
Yeah, it's like graduating. Right. Okay. So,
Do this. Elimination time.
elimination reactions.
So this is also called dehydration.
Elimination reactions of alcohols are also called dehydration reactions. The reason is because if you have to eliminate by pulling this off, you end up pulling equivalent of water off of the molecule, which gives you the double bond. So elimination reactions of alcohols are dehydration reactions as well. Yeah.
I think we wanted the hydrogen anti-steric
Yeah, this is not sterically correct. Yeah, this is me just generally saying. I put them next to each other so I could circle them together to show that there's an H2O there. So let's see here. The way this works is you need an acid catalyst and you need heat. So let's say we've got some secondary alcohol here, cyclohexanol, and you can use any number of acids, but sulfuric acid is most commonly used because it's a strong acid and it's also an oxidizing acid. So sulfuric acid, heat to reflux, and this yields, this is a product. However, it is reversible. Now, to help make this reaction go more aggressively to completion, if you think about physical properties, alcohols typically have fairly high boiling points compared to alkenes because they have higher intermolecular forces because of the presence of these lone pairs and the ability to hydrogen bond from this oxygen to the hydrogen on another cyclohexanol. So when you remove this, boiling point drops, which means at heat, you can distill the product off the reaction mixture, collect it separately, and because you are pulling the product out of the reaction as it is being made, it keeps making product because it's trying to reach this equilibrium. So you can drive this towards completion via Le Chatelier's principle by distilling the product as you go. So this is a reversible reaction, but we have ways we can pull the product out in this particular case. Different mechanisms. So we can use an E1 if, what are the criteria for E1 in terms of the primary, secondary, tertiary?
If it's a primary or
Mm.
no secondary, tertiary.
So you can go with the E1 mechanism here because you can, well, let's look at the mechanism. So we've got our sulfuric acid. We're going to protonate just like before, and now we have a secondary alcohol, which also is now an excellent leaving group because of the protonation, so this can spontaneously leave, giving us water. And then what's the rest of the mechanism look like? We need something to come in this case, water, pull the proton. We can do this because this is regenerating the acid catalyst. Breaks this bond, pushes the electrons between, and that gives us our double bond. So, just like before, identical mechanistically, following the initial protonation that made the hydroxyl group a good leaving group. So, let's see here. If we've got something like this, we would have the ability to do different products because we can pull protons from here in the last step, or here, or here. These two will give the same product because whether it's double bond here or double bond here doesn't matter. It'll be symmetrical. This is a different product, however. So we're going to have two possible products. So even though this can occur at two different locations, it's only 16%, this one is 84%, and that is because this reaction favors the formation of the more stable product. Because it's a reversible reaction, so the thing that favors stability is going to be preferred because it's going to form more of it in a reversible system. Now, as a caveat to this, this is E1, right? So what does that involve in one of our high energy intermediates? Form a carbocation, right? So what if we've got something like like this. Everybody go ahead and take a minute to try to predict what might happen if that reaction were to occur. First thing first, just predict the carbocation and then go from there. I'll rewrite this over here a little bit so you guys have some room. Secondary carbocation, tertiary carbocation.
Even though it's just because like when we were going over that, would we like even though it would be major for the tertiary, would we still have the other like should we definitely document it?
If you're asked for the major product, you don't have to do this. This is only going to be 3% yield.
Okay.
Good. So, before we do the methyl, let's go ahead and take a look at this one. This is fun. So, to walk through, the first step is we'd have our acid catalyst. The hydroxyl group reacts with the acid, kicking off water. It's going to be OH2+, which then can act as a leaving group, and we get our carbocation. If we don't have a methyl shift, this is our product. Why is this our product? And not putting the double bond in a more substituted location.
H, there's no H.
Right. There's no hydrogen over here to pull off to do the dehydration. So, we don't have a hydrogen here to do it, we can't put it here. We have to take it off of this carbon, which is why the double bond goes here, which makes it even a poorer product, which is why it's only 3% product. Over here, however, we have these 6 protons that can do it, as well as that proton. So we can reversibly make this product and this product. Which one should be favored? This one? No. this one. So if you're asked to do the major product of this kind of elimination reaction, this would be the clear winner because it's the more substituted, more stable product following the methyl shift. And in this moment, you're thinking, man, I sure hope there's a way that we can do that reaction without just acid. And you'll be right, there is. Did I skip it? Stable product, dehydration reactions. Okay, cool. But we will get there. So any questions about this before moving on to E2 reactions of alcohols? No? Okay, so for the E1, tertiary is better than secondary, is better than primary. This is functionally a no-go. For E1, tertiary is highly preferred, secondary is okay. We can make it work partially because in this case, we can distill off the product, so we can make it go, and we can add some heat to it to get that distillation going.
Wait, we're talking about E1, not, okay.
For E1,
Okay.
tertiary, secondary, primary is off the table. For E2 of primary, you can get some competition with SN2 and formation of an ether. So we're going to look at that real quick. However, elimination is preferred. So a bit of SN2, but elimination is preferred. So this is kind of the reality of doing organic chemistry. Very, very frequently there will be less desired byproducts of the reaction that you just have to clean up after your synthesis step. So pretty much all synthetic schemes involve synthesis followed by cleaning things up and purification steps. So that's just part of the game, depending on the tools you have at your disposal. So for E2, let's see, we've got CH2OH, and we can do this reaction with sulfuric acid and heat. So the setup's exactly the same, but the mechanism is different because I'm just going to do, let's see, that's our acid catalyst. You can use sulfuric acid if you like, or you can just use sulfuric acid that's formed hydronium. Either one works. Now we have a great leaving group, whereas before we did not have a good leaving group. And we can now have whoa. Here we go. Okay, good. Let me redraw this. So is water acting as a nucleophile or as a base in this reaction? We have some votes for base. Votes for base. Votes for I haven't the foggiest. I have some but I want to point out lots of very tentative votes for base. There wasn't the like Hermione like, ooh, call on me. It's base. It was like, please don't ask me why, maybe. Votes for nucleophile. Because it's an elimination and you're abstracting the proton, right? So bases like to donate their electrons to protons. Nucleophiles like to donate their electrons to electrophiles, which can be protons. But because we're not doing a nucleophilic attack, we are grabbing this to reform our acid catalyst. Son of a gun, that's the wrong way to push that. And I even attacked the wrong hydrogen.
What have you done?
Right, the wormhole opens and swallows me. Takes me to chemistry purgatory.
It takes from the hydrogens from the beta carbons, right?
There we go. Yeah, has to be the beta carbon. Or else we'd be forming a double bond oxygen. That would just be silly. So, we've got our product. Now, we talked about SN2 being an issue because it could be.
Wait, so is a nucleophile on base?
Oh, son of a gun.
I was like, now I'm real
Okay.
confused.
Oh, you want to get confused?
Oh, God.
Oh.
Yeah. That's what's up.
Can you not?
So in this case, if this let's say this was ethanol, because we have ethanol in our reaction.
And that's the competition with the SN2 then.
Yep.
That's what's happening right now. Nice use of 2 colors.
Yeah, use of colors. So, and yeah, we have a diethyl ether as competitive product here. So we have our elimination. We also have our substitution. Sorry, dehydration. Sorry, there was a question?
Yeah.
Going on, so we need to do the SN2 as well.
Not if you're asked for the favored product, because the favored product is going to be the elimination.
Yeah, how did you get an ether in the? I have like.
Did you just add the nucleophiles for the I can't see now.
Got it.
Oh, okay.
And then you have the second attack coming back, reforming the acid catalyst to pull that off.
X is a nucleophile itself.
Got it.
So if we just written MU next to it,
Yeah.
Yeah.
and the product.
Yeah, I thought that for some reason.
And this can't act as a base because it's a terrible base, but it is an okay nucleophile. So, competitive process.
Formation is computers.
Let's see. Yes. You're first.
So the base
It's going to be, in this case, water or ethanol could be the base also. Yeah, either the ethanol or the water could be the base in this case. No problem.
So when you have these alcohol solvents, are you going to have deprotonation problems where you're making like ion?
Alkoxides?
Yeah.
Only if you have a really, really good base pulling those protons off. A really, really good base, which we don't have here. Because we're doing this in an acid. So you're definitely not going to see deprotonation of the alcohol there. I think we should pick this up. This is a good spot to pick it up next class. And we'll go from there. Any other questions before we call it? Well, extra time to ice skate across campus. Okay.